Hey pre-calc, as you can see, we are continuing the search and the hunt, and we're digging for roots. We're up to digging for roots day 4 now, and there are still more tricks to be learned. In fact, a lot of tricks today. Today we're going to shorten our synthetic division, and it's not really a shorter process. It shortens the amount that we write down in synthetic division, so you'll see that happen at some point in the notes. We're going to talk about some other theorems that help us to reduce the amount of work that it's going to take to eventually determine all of the roots of these polynomials. So for the first one, we'll start with that real quick. It says show that 1, 2, and -1 are roots. There's an example similar to this at the end of the last set of notes where we tested 3 roots in a 5th degree polynomial. Eventually we get it down to a 4th degree. So let's go ahead and copy the coefficients right from the start. Okay, so bring down the 4. 4 times 1 is 4, plus -15. It's going to be -11. Times 1 is -11. Plus 8 is -3. Times 1 is -3. Plus 19 is 16. Takes a little while to get down to the end, but we're getting close. That's going to be a 16. Add it to -12 to get 4. Times 1 is 4. And in the end, you do confirm that, yep, 1 is definitely a root. Okay. So maybe I'll try and sneak my work in here. Actually, you know what? I'm going to get real sneaky here. I want to test 2 as a root, but I just want to use these coefficients now. Remember that these are the coefficients of a 4th degree polynomial. Okay, so rather than rewrite those all again, why don't I just use that list, bring down the 4. 4 times 2 is 8, plus -11 is -3. Times 2 is -6, plus -3 is -9. Times 2 is -18. Plus 16 is -2. Times 2 is -4, plus 4 is 0. Okay, and now we've gone from a 5th degree to a 4th degree to eventually now a 3rd degree. And the last root that I'm given that we should be testing is -1. So I'm going to carry my work over here. I'm going to test -1 in the coefficients 4, -3, -9, and -2. I'm going to bring down the 4. 4 times -1 is -4, plus -3 is -7. -7 times -1 is 7, plus -9 is -2. -2 times -1 is +2, plus -2 is 0 one more time. So the nice thing about this is we've gone from a 5th to a 4th to a 3rd to a 2nd degree polynomial. This process, by the way, is called depressing the equation. Okay, depressing means we're creating something that's now 1 degree less each time than what I started with. So remember that this would be the coefficients 4x squared minus 7x minus 2. And if I set that to 0 and solve this, we should be able to find the remaining 2 roots, because for a 5th degree polynomial, we need a total of 5. And we have 3 of them already. So to get the last 2, we want to figure out, is this in fact factorable? If it is, that's the quickest way to get the roots. And it turns out that it is nicely factorable here. If you put a -2 here and a +1 there, the outside multiplies to -8x, the inside to 1x to give you a total of -7x in the middle. You can get that from box method or slip, divide, slide. So the other roots are at -1/4 and 2. Now what's interesting about this one is that x equals 2 was also another root that we found earlier. So 2 winds up being a double root of this polynomial. The fancy word for that is it's of multiplicity 2, and then the others are single roots at -1/4, -1, and +1. So we're able to determine all 5 roots using synthetic division. Eventually, though, we have to come up with a way to know what we should be testing. So far, I've been giving you that list of roots, and that's coming. Okay, that's one of the last tools that we'll learn. Yeah. Let's go ahead and take a look at this next one. P of x equals 2x cubed minus x minus 4. It says find P of 4 and P of -1 using synthetic division. So the remainder theorem would just allow us to plug 4 and plug -1 in for x, but it does say to specifically use synthetic division. I am going to use the shortened method of synthetic division. That was kind of what it said we were going to do at the start today, the shortened synthetic division. And it takes a little while to get used to this. So you're not going to like it at first. I know that going into it. You're all going to complain about it next time I see you. And you're going to ask, can't we go back to the old way? And the answer is no. But I promise you'll get used to it, okay? You're going to set up a chart, and in the left column, you're going to put x. And then what you're going to do is underneath x, you're going to write 0. Because what happens is if you test 0 with synthetic division, you actually just always will get the coefficients of the polynomial p of x. So the coefficient of x cubed is 2. Coefficient of x squared, remember that's missing, and we do need a 0 as our placeholder there. -1, and then finally -4 goes at the end. Remember that -4, the remainder that we get, that's the same thing as the y value, or f of x in this case. I guess we can call it p of x, but traditionally I feel like I always just call it f of x here. All right, so this in the end, when you get that remainder, I want you to separate that in its own column because this is the y value that goes with this value of x. And this will be helpful in order to determine roots and some other things that we want to pay attention to find the roots efficiently. So how do I find p of 4? P of 4 using synthetic division. Here's the only trick. We're not going to write down this in-between step, right? All these numbers, when I did 4 times 1 and I wrote it there, I'm just going to take 4, add to -15 in my head, and write down that -11 that we got in that spot. So I'm still going to be writing down these numbers right here, but I'm not writing down the row of in-between work. So that's the big difference here. So let me show you how it works. You're going to bring down the 2, no matter what. Bring down that first number. 2 times 4 is 8. Add it to the next row. 8 plus 0 is 8. Just a little bit more work in our head now. Okay, 8 times 4 is 32. Plus the -1, 31. Hardest part about this will be doing the last product here. 31 times 4 is going to be 124. 124 plus that -4 is 120, a very large remainder there. Okay, that's the y value, though, that goes with the value of x at 4. 4 is most certainly not a root. But we also want to find p of -1. So for testing a new root, you don't have to rewrite all those coefficients again. Just leave them up at the top. But we are going to start by bringing down the 2. Okay, so you're always multiplying by this root, add it to the next column. 2 times -1 is -2, plus the 0 up there is -2. -2 times -1 is +2, plus -1 is 1. Finally, 1 times -1 is -1, plus -4 is -5. So there's a couple of interesting things that are happening here. One of them being, when you see some of these sign changes happen from a negative remainder or a negative y value to a positive y value, we know that there's roots that exist in between these values, right? So I know that there's some sort of root happening between 0 and 4 because the sign changed from negative to positive in terms of the y value. So we have to cross the x-axis somewhere from 0 to 4. But that's actually not even what I was trying to get at here. What I'm trying to get at is says, what do you notice about the signs of the rows? So what I mean by that is when we tested +4, notice how all the signs of these numbers are positive, 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 positive. All the numbers in your synthetic division are positive there. So what does that mean? It means that 4 is an upper bound of the polynomial p of x. What does it mean to be an upper bound? It means that there are no roots higher than x equals 4. So this is a good point, because if I test 4 and I get positive, 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 I know automatically that I shouldn't go next and test 5 or test 6 or test 7 or test 8 or anything above 4 or even 4.5. Okay, so when you find upper bounds in synthetic division, it's kind of a good hint that there's nothing greater than that possible as a potential root. And it says for upper and lower bounds to see the sheet. This sheet is not in your packet, but I'll go over this maybe again in class tomorrow. There's another sheet that has all of this in your packet, but not this one specifically. So if we use synthetic division to divide by specifically something where the root is positive, and we obtain a row containing all positive numbers, then that value is an upper bound for the real roots of f of x equals 0. And the main idea there, again, is don't test anything larger than that. So for lower bounds, should we expect all negatives? Not exactly. If we use synthetic division and r is a negative number, the root that we're testing, we're going to look for the numbers to alternate back and forth between positives and negatives. And if that's true, then R is a lower bound. So let's go ahead and take a look at this negative root that we tested. We tested a negative, and those signs alternated positive, negative, positive, negative. So when that happens, we know that -1 is a lower bound. So we tested a negative number, namely -1. And the signs went plus, minus, plus, minus. So when the signs alternate like that, -1 is a lower bound for P of X. So what does that mean for us? It means we're not going to test -2 or -3 or -4 or anything that comes before -1 because I know already it's not a root according to that upper bound and lower bound theorem. Doesn't seem like a big deal that's going to help us yet, but I promise you it is. We're going to start finding them within our work of synthetic division and be like, okay, great, I know I can eliminate a bunch of possible roots by identifying when things are upper bounds and lower bounds. Okay. What I really want us to do is start exploring those ideas a little bit more and take a look at finding the roots of this polynomial right here. In order to do that, I think we need a little bit more practice too with the chart of synthetic division. So I'm going to set up the chart by making this big column on the left called X. This is where I'm going to test all my roots. You'll always start by putting a 0 first as your initial root to test. The coefficients of the polynomial are 4, -8, -15. And that last number of 9, remember that's actually the remainder, which corresponds with f of x. Okay, and all the roots that I test, so I'm going to come back to this row right from the top. These are the original coefficients that I'm testing, all of the roots that I'm about to show you. Okay, let's start with good old x equals 1. That sounds like a good guess. So I'm going to bring down the 4. 4 times 1 is 4, plus -8 is -4. -4 times 1 is -4. Add it to the -15 to get -19. -19 times 1 is -19, plus 9 is -10. Well, the conclusion is 1 is definitely not a root. Is 1 an upper bound? Did I get positive, positive? Nope, definitely not. But what I do notice is that when I test 0, the output is 9. When I plug in 1 for x, the y value is -10. So when you see a sign change, according to what we did a couple days ago with the root location theorem, there's a root between 0 and 1 for sure. Definitely a root. So the most likely number that we probably guess next is a half. Hopefully 1/2 works. Let's check it out. So bring down the 4. Half of 4 is 2. 2 plus -8 is -6. Half of -6 is -3, plus -15, -18. Half of -18 is -9, plus 9 is in fact 0. So we know that we found a root at x equals a half. Traditionally, you would stop here and say, hey, this is a quadratic. It's 4x squared minus 6x minus 18. And you would go ahead and solve the quadratic to find the other 2 roots that we still have left. But to show you some other things that happen with synthetic division, I'm going to pretend like we didn't actually just find a root. Okay, so even though we could stop here technically, I'm going to keep going and I'm going to test everyone's favorite value, x equals 4. Okay, so if I bring down the 4, notice how this whole first column is a bunch of 4s here. 4 times 4 is 16. 16, just make sure you're coming back up to the top always. 16 plus -8 is 8. 4 times 8 is 32. 32 plus -15 is 17. And 4 times 17 is 68. 68 plus 9 is going to be 77. Definitely not a root at x equals 4. But what I do know is I tested 4 and we got a whole bunch of positives. Positive, 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 positive. So that means that x equals 4 is an upper bound. So if I was going to make random guesses at my next root, I wouldn't test anything above 4. Not 5, not 6, not 7, any of those. So maybe I'll drop back 1 and I'll test x equals 3. Bring down the 4. 4 times 3 is 12, plus -8 is 4 again. 4 times 3 is 12, plus -15 is -3, times 3 is -9, plus 9 is 0. So we found our second root. Okay, we have one more to go. let's test a few others here. If I test -1, bring down the 4. 4 times -1 is -4 plus -8 is -12. I'm picking up the pace here. -12 times -1 is 12 plus -15 is -3. -3 times -1 is 3 plus 9 is 12. Forget doing double time on these videos. You might have to like slow me down. I don't even know if that's an option on YouTube. Okay, that didn't work. Let's test -2. Bring down the 4. 4 times -2 is -8 plus -8 is -16. -16 times -2 is 32 plus -15 is 17. 17 times -2 is -34 plus 9 is -25. Okay, well, -2 is definitely not a root. However, there's a lot of things that just happened there. I tested -2. Look at those signs. Was anyone even thinking about that for -1 there? The signs go positive, negative, positive, negative. So the conclusion here is that x equals -2 is a lower bound for this polynomial. I don't have to test -3 or -4 or -5 or -6, any of those, because I know that they're not possible roots. Something else pretty big happened. Did you catch the other thing that happened? Test the -1. The y value is 12. Test the -2. The y value is -25. When you see that sign change, there has to be a root in between -1 and -2. So what's a good number to test between -1 and -2? Maybe like -1.5 or -3/2 if you like fractions like me. Okay, here's the grand finale. I really hope this works. Bring down the 4. 4 times -3/2. Well, 2 goes into 4 twice. 2 times -3 is -6. Plus -8 is -14. A little bit tougher in your head to think about this, but we got it. 2 times -14 is -7 times -3 is 21. 21 plus -15 is 6. And finally, 2 goes into 6 3 times -3 is -9 plus 9 is 0. We found our third and final root. So, I mean, this is a really good look at our new synthetic division chart. All of these tools that we've been talking about now for a few days, but specifically the new ones today, we can identify upper bounds, we can identify lower bounds, these sign changes. It's all going to be critical info to narrow down the process for finding the roots of higher order polynomials. Okay, so if you're feeling okay about that, on the next page, first and foremost on the next page, there's actually a typo at the very top. Somehow we have x to the 4th, x cubed, and then x cubed again. It was supposed to start at x to the 5th. And then this term is supposed to be x to the 4th. So if you want to change those for me, we can go ahead and do that. And then we get our x cubed, x squared, x, and constant there. So the directions say find the first positive integer that's an upper bound and find the first negative integer that's a lower bound. Okay. We're going to do this in class tomorrow. So there's something just like this on the homework, and I think if I model it with you in class using our new synthetic division chart, just to really make sure we're understanding that, we'll make sure that when you get to the homework on this, that it will make that much more sense. So we're going to wait a second on that. Okay. But the last thing we're going to talk about in today's lesson is something called Descartes' rule of signs. This is another tool, yet another way to help us dig and uncover all of the roots. Descartes' rule of signs tells us the maximum number of positive and negative roots that we would expect these polynomial functions to have. And it says to see the sheet, and again, this is not in your packet, this direct sheet, but there is eventually a sheet that summarizes all of these tools. Okay, so here's what Descartes' rule of signs says. The number of positive roots is equal to the number of variations in the sign of f of x, or can be less than that by an even integer. We're not going to even really talk about that piece of it as much today. The less than that by an even integer, we'll recap that over the next few days. But the number of negative roots is equal to the number of variations in the sign of f of negative x, or less than that by an even integer. And finally, in Descartes' rule, a 0 is ignored. So what I mean by that, you know, we put zeros for placeholders with synthetic division. We don't need zeros for Descartes' rule of signs. Okay, these might sound a little confusing to you about what we're actually looking at, so let me help you make some sense of it by looking at this first example. So we have the function p of x. I feel like, do we need a light? It's probably too late for that, but I don't know if that changed anything at all for you guys, but we'll focus it. Yeah, we'll do some of those things. Okay, first thing I want us to do is I'm going to write underneath the polynomial p of x again. But instead of writing the whole polynomial out, I just want to look at the signs of the coefficients. Are they positives or are they negatives? So x to the fourth is positive, x cubed is negative, x squared is negative, x to the first is positive, and then the constant at the end is negative. Okay. So what I want to do is I want to analyze how many times did the sign change? How many variations are there? That's what the rule says. It's equal to the number of variations in the signs of f of x. So how many variations were there? Well, from the first term to the second term, we changed sign once. It went from positive to negative. Then we go negative to negative, no sign change there, but then we go from negative to positive, and then positive back to negative. So there are 3 sign changes in p of x. And what this tells you, it is the max number of positive roots that p of x can have. So at the most, p of x can have up to 3 positive roots across the x-axis in 3 positive places. It may not actually do that, but that's the maximum number we would expect. So then we have to write down something called p of negative x. To figure out the maximum number of negative roots that this could have, we're going to consider what would the signs look like for p of negative x. So p of negative x would say, let's plug in a negative x everywhere we see x. And we've done that before with symmetry tests, haven't we? We've replaced all our x's with negative x's and then determined kind of what the resulting polynomial looks like. What you should remember is that when you replace a negative x, if there's being raised to an even exponent, the coefficient's not going to change. Negative x to the fourth would still become positive in the end. But if you raise a negative x to the third power, that's going to change from negative to positive. So when you do p of negative x, only the coefficients of the odd exponents change. So x to the fourth doesn't change. X cubed, yeah, when I plug in a negative there, it's going to change that sign out front now to positive. X squared is even, so it stays negative. X to the first, that's odd, so that's going to change to negative. The constant at the end will never change. It's technically next to x to the 0 if you want to think of it that way, which is not an odd exponent. Okay, but yeah, the constant actually will never change, so we'll just leave that as negative. How many sign changes do we see here for p of negative x? I'm only seeing 1 in the middle here, right? Goes from positive to positive, no change there, but positive to negative, and then stays negative the rest of the way. So that 1 sign change that we're seeing, that is the maximum number of negative roots that this polynomial might have. So the way that we summarize this information is you're going to make a chart off to the side that has 3 columns, P and C. And I think you know what positive is P. I'm pretty sure you would assume that N means negative. What does C stand for? C are for complex roots, right? We're only talking about real roots when we talk about positives and negatives. C would stand for any roots that might be complex in A plus BI form. So I know we have 3 positive. I know we have 1 negative. If there's 3 positive roots and 1 negative root at a maximum, how many complex roots would there be? Well, for that first case, there would be 0 complex. Why do I know that there's no complex? If you're dealing with a 4th degree polynomial, x to the 4th, the max number of roots that you can have is 4 roots. So if you happen to have 3 that are positive and 1 that's negative, then there's no complex, nothing in the form A plus BI. And I promise we're doing more like this in the next lesson. So if this is a little confusing, I get it, but we're going to definitely make some sense of it. Promise. Okay, let's try one more together just to really make sure we're good with this concept. If we look at this example, we've got our function p of x. Now notice how p of x is a 5th degree polynomial, so we're definitely missing the x to the 4th and the x cubed terms from that polynomial. But it says in Descartes, a 0 is ignored in Descartes' rule of signs. So we're going to write this as positive, 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 negative. Those are the 4 signs that I see in p of x. And the sign changes just once at the end there, right? Only one little sign change in p of x. Let's talk about p of negative x. Okay. For p of negative x, we're only changing signs if it has an odd exponent. X to the fifth is odd, so that's going to make this negative. X squared is even, keep it positive. X to the first is odd, so change that to a negative. The constant never changes, it stays negative there. How many sign changes? One in the beginning, negative to positive. Positive goes back to negative, but no sign change at the end. So there are two sign changes for p of negative x. And then finally, we have to then summarize this in a chart for positive, negative, and complex cases. Okay. So we have one positive root at a max. That's the most number of positives. At the most, we can have two negatives. And then last but not least, for complex, do we have any? Well, we're going to have to. If this polynomial has 5 roots total, and I only have at most one positive and at most two negative, we definitely have two that are complex to get a total of 5 roots. Okay, so sometimes the sign changes already add up to the max number of roots, which is 4. But if they don't, these two max values, we need at least as many more here to equal the total number of roots, which is 5 for this example. Okay, that is it for this lesson. Again, we'll go back and recap this example tomorrow together in class. You'll probably have a lot of questions for me, and I hope you do, because we'll go over anything that you might need some extra help with. But have a great rest of your day.